better with the microphone. We'll say a few words about the MAC layer to finish with it, and then we'll start studying the transport layer, which is one of the most important layers one of the most visible ones in the internet. The last thing we haven't discussed yet about the MAC layer is the security aspects. MAC addresses are in principle sent in the clear, which means that it gives a lot of possibilities for attackers to do things like hearing someone else's data, if you want to sniff and obtain intelligence about what other people are doing. This is perhaps the most important problem if you connect to a public hotspot and all the data you send are in the clear and they're available to everyone. What should you do in such a case? Point-to-point encryption. You have to make sure the data you're sending is encrypted. It can be, if it's not encrypted at the MAC layer, you have to hope it is encrypted at a higher layer. There are, we will see a bit later, two different ways to do encryption when it's not done at the MAC layer. The most frequent one is at the application layer. If you use HTTPS, if you go to a secure HTTP site, then there will be encryption of all the data you're transmitting. But not everything will be encrypted. In particular, the transport headers will not be encrypted, so people will be able to see to which site you go. If that's not of a concern, that's fine. Other options are to use network layer encryption, which is, for example, what you do when you tunnel your information through what is called a VPN. If you access the EPFL network from the outside, you can access it from in the clear or through a VPN. When you use a VPN, all the data you're sending to EPFL through the hotspot, for example, is encrypted. Most applications today use encryption, except notably for the web when it's not HTTPS but HTTP. So if you go to a website and it's not an HTTPS, everything you will be sending is visible to everybody if there is not a lower layer implementing encryption. Email, in principle, is also encrypted, depending on how you tune your email parameters, but most services require encryption, so that hopefully there would be higher layer that can protect you. Yes? Pardon me? Telnet is not encrypted. Telnet is just plain text, so you should not use it. You should use, what should you use instead? SSH, exactly. You should use the encrypted versions of Telnet, and you don't use Telnet apart from extremely rare cases when you connect from a device that's directly connected to your computer because you're debugging it or something, then you can use Telnet for that. But in principle, we don't use Telnet anymore. If you do it, you're probably an attacker of some kind, or you want to induce people into being attacked. If you have a Wi-Fi at home or at EPFL, you also want to prevent, you want also to do some form of access control. So you want to prevent free riding. You want to prevent any non-legitimate user to gain access to the network. So that's one of the things that is not done by the plain MAC layer. And you may also want to avoid people forging MAC addresses. All of this at Ethernet, on Ethernet cables at EPFL is not done. So it's similar to what happens with ARP. It's not done. There is no security other than monitoring. Everything that happens is monitored, or the MAC addresses that are present are monitored. If there's a change of MAC address on an Ethernet port of a switch, this is logged. Most of the time it produces nothing, but if there was a proof of an attack, the logs can be used to trace back what has happened. That's a weak protection. Wi-Fi is in principle more protected. If you use Wi-Fi at EPFL, then there is, as you know, if you use the EPFL Wi-Fi, not the public Wi-Fi, then there is access control, authentication, and encryption. Access control means you need to first give your credentials, your CamiPro name and your Gaspar password. And once this is done, the result of this initial phase is that cryptographic keys are set up, secret keys are set up between the infrastructure of the wireless LAN of EPFL and your device that will encrypt all the data and also authenticate it. In particular, if someone else comes from your machine with your MAC address, and when you have authenticated, the system has learned what is your MAC address, so this will be associated with you temporarily as long as you're in this session. And any packet that comes with a different MAC address from you or from someone else with your MAC address would be detected and not accepted. Encryption also gives you some form of protection against eavesdropping. You may have heard that recently, I think this week, a few days ago, there was an attack against the security mechanism. So there is a weakness on some of the protocol that is used to set up these things that may make it a bit fragile. But in principle, this is how things are secure. At home, you probably use password protection, which is a weaker form of protection that does not authenticate really who you are, but just make sure that whoever wants to connect to your network knows a password. And usually that is not associated with a given MAC address, but simply is used to provide a form of encryption and therefore access control. So assume here Bart connects to, who is an EPFL student, connects to EPFL. Yes, question?
Yes, I have a question about this. The recent days, I've heard the news that there is some technical failure in the EPA2 protocol.
Yes.
Do you have any comments about this? Is it a big security failure or?
I don't have a serious comment about this. I don't know exactly what's the attempt of what's the extent of the threat. My hope is that this weakness was known already, so updates have been performed by practically all operating systems to prevent this if you regularly update your operating system. That's a guess, not an educated one. So you'll have to check by yourself. Yes?
And the systems under outdated devices. So there is a list of updates. So usually it's patched for that. So yes. So they figured out before they published the result that it's broken. They gave a period of like 1.5 months or 3 months for the vendors to patch it.
Yeah. So it's the usual procedure. When a vendor finds a weakness, they first patch it, and they are good citizens. They also inform the CERT, which is one of the centers that monitors all the security problems, so that the industry can first fix the problem, and only then you make it available to a large public. Another question? No. So let's come to my question now. Assume Bart and Lisa are not able to break the authentication phase of Wi-Fi, but they do the simple trick. Bart is an EPFL student. Lisa, as you know, is his sister, is visiting and would like to connect to EPFL. So Bart, who took this course, sets up his PC as a bridge. Right? We can, with a Linux PC and even with other systems, set it up as a bridge here. Will it work? I close the poll in 5 seconds. So the majority says it doesn't work. By the way, if we reverse the role of Ethernet and Wi-Fi, This might be a way if instead of Ethernet it's a USB cable, and instead of a PC, if this is a smartphone, this is one of the things that we commonly do. If you have access to one network with a smartphone, then you can share this connection. That's what some operating systems say. Other systems say tethering. So can you share the connection in this way? And the correct answer is no. By bridging, it will not work. Right? And what's the reason? The reason is the authentication that is typically done in this and other settings. The MAC address, if you do bridging here, the packets sent by Lisa will appear to the Wi-Fi station with the MAC address, source MAC address M3. Because that's the name of the game with bridging. Now this, the base station or the controller that's behind the base station will not accept this. It will say coming from so the software here will have to authenticate it, but the MAC address will not correspond. So there will be the tag that is computed by the authentication does not correspond to the MAC address, so it will be dropped and it will not work, which is what you want after all. You want to prevent access.
Can you still access to NAT?
That's the next question. So next question is exactly this one. If you now, the majority says yes, and this is probably the truth. I say probably because you're never 100% sure in this domain, but probably this should work. This is the solution that is implemented by a smartphone when they do connection sharing. They NAT, in fact. And the reason it works is when you NAT here, everything that comes out of the NAT appears to the outside world as if it would come from this machine. It has an IP address of this machine, therefore also a source MAC address given by this machine and a port number that is different, but there's no way for an outside system to know whether there are multiple processes on this machine or physically a computer connected to this. So this will work. In passing, observe a side effect of NATs. I mean, the NATs violate the architecture. Because they violate the architecture, they can help you also violate a number of security measures that are based on a view of the architecture. Question?
Now we are connected to the Wi-Fi together and want to share our connection to the Wi-Fi. That's not possible. But why?
If you're connected to the Wi-Fi of EPFL and you want to share it, and it's not possible, you mean it's not possible with the smartphone that you have now? Because some smartphones, I think it will soon be possible even in iOS. Some smartphones share it only from a cellular telephony. They share it over Wi-Fi, so they don't accept to share Wi-Fi over something else. They use only Wi-Fi as this link here. But it's a limitation of the operating system. It's not a fundamental thing. There's no reason to do it. Typically, they want to share a connection that you have not from Wi-Fi, but from a cellular operator. And the problem is exactly the same here. Your cellular operator will not, if you bridge here, will not like it. But sooner or later, this will be also available. It will be a new, fantastic added value of the iOS 12 or whatever. That's what we will see of the MAC layer. So the MAC layer is either shared medium or based on bridges. Bridges can be present everywhere. And the important thing to realize is that today we have in fact two networking layers, the MAC and the network layer, which is a bit surprising when we start analyzing how things are, is given by history. So you could say, well, but this is computer science. In computer science, we move things very rapidly. Well, it turns out that in the computer networking world, things move very rapidly in terms of application. Facebook came very suddenly and then was widespread within a year. But the networking layers themselves, they move very, very slowly. People use the word fossilization of the networking layer. So all the devices that operate, including the NATs that you and I have at home, changing them is of course possible. You and I can change your NAT, but if you are developing an application, then if you require all NATs to be removed or to be changed, or the network layer to be changed, then it won't work. Your application will not work. So any application developer has to develop an application that will work with the existing internet. That's a chicken and egg problem, because it has to work with the existing internet. The existing internet is happy to be as it is because everything works with it. So there is no incentive for anyone, in fact, to change the way the networking layer is, other than in an incremental way that is backwards compatible. For example, the MAC layer, we could very well say that if I have IPv6 only, if you think about what we do with IPv6 and Slack, we use the MAC address to create a linked local IP address. So we could very well say, well, let's use the linked local IP address as your universal, the equivalent of a MAC address. Perhaps that will come in 50 years, but for now we're not yet there. Yes?
So access control for MAC. Is it quickly done? So the router discards the MAC packets. Can we flood the, let's say, router with unauthorized packets and to slow it and turn down?
It's not the router, it's the Wi-Fi, the Wi-Fi base station. Sees whether there is a authentication tag that corresponds to the MAC address that it has in its table for the authentication token.
Can we flood it with unauthorized requests?
Probably by flooding, yes, you can prevent access to the network. You can jam also the signal. So yes. Other questions? Then if there's not, we move to the next chapters, which is the transport layer. So the goal of the transport layer is to transport your data, so that's to provide a programming interface to programmers. And in TCP-IP, it exists in TCP and UDP. So TCP/IP is called TCP/IP and not TCP, UDP/IP, because that would be awkward. But UDP is really part of the landscape here. So the transport layer is, in principle, in end systems only. When A talks to B, there are routers and bridges along the path and base stations. All of those are not involved with the transport layer. In principle. In practice, there are always hacks that people do, like we see that a NAT all of a sudden looks at the port number of the transport layer and changes it. So this is where the principles are violated. There may also be what are called transport layer proxies, where the data that you send is in fact not sent directly to the end, but to an intermediate system for whatever reason. We'll talk about that a bit later when we talk about proxies. But in principle, you'd like to avoid them. In TCP, there are, I say mainly, but practically only exclusively two transport layers, UDP and TCP. The transport layer is typically implemented in the operating system. So if you want to change the transport layer in your smartphone, you have to do an update of the operating system, which for some smartphones is easy, for others is more painful and risky, because when you update, you don't choose what you update. So you have to take the latest version of the operating system, which you might not like, because your system will become very slow. In other words, the transport layer is something that's fairly deep in the machine that you don't change in principle whenever the application does not like it. For example, if you're Google and you are streaming data to millions of users or hundreds of millions of users, so burning a significant fraction of the capacity of the internet for that, you may be interested in a better transport layer than TCP for this. As we will see, TCP is not necessarily optimal for everything. So you would like to develop your own. And there has been a number of attempts to develop your own transport layers. That's why I say mainly there are other transport layers that have been proposed. None of them has become popular. So in practice today, something else is happening, is that higher level protocols, the application layer, is constructed intermediate systems, intermediate software called middleware that will replace TCP, for example. We'll talk about that when we talk about the application layer. But such a thing would be running on UDP. So take home message for today. Any application program, including the middleware that's in it, typically today runs on UDP or TCP. Other cases are really exceptions. Fortunately, there is not a TCP v6 and a TCP v4. There's only one TCP. So TCP and UDP is not affected by whether we have IPv4 and IPv6. That's the good news. A few words about UDP, which is really simple. We have already discovered that there are ports. So what are the port numbers? When I use UDP, typically I have multiple processes on one machine that talk to, so we have multiple processes on one machine. One of these processes, for example here a DNS resolver, speaks to another process on some other machine, but on the other machine there are also other processes. For example, you may have your client resolver that's talking to the web server, to a DNS server that is here, but the DNS server may have other things. For example, you can SSH into the DNS server, or you can look with HTTPS what is the status of the DNS server. So the DNS server will have a number of other processes that are used for maintenance, for updates, etc. In order to recognize which sub-entity inside the machine we're talking to, we use port numbers. For example, here, when I do a DNS resolution, my software will use a source port number, 1267, and a destination port number, 53, and UDP contains those port numbers. So inside the UDP header, there will be the source and the destination port, which is the essential information that's contained in a UDP header. The UDP header is part of the IP payload, so it is contained in the IP message. And the port number 53 is well known. Those are typical server ports. So if you do a DNS server, in principle, it is listening to port number 53. If you don't know it, if you talk to a server that you don't know which port it is listening to, you have to find the port numbers through DNS or through some other mechanisms, through a link on a website. But fortunately, for classical services, the port numbers are predefined. That's the so-called lower numbers. Higher numbers, like this one, are typically temporary. So when my host here creates a process, it asks the operating system for a port number. The operating system gives it the next available port number, and then it is used by the receiving host, here the DNS server, to know whom to respond to. So when this guy will respond with the answer to the DNS query, the destination port number will be 1267, so the operating system will know which process should receive the information. There are a few things in the UDP header that we will not discuss now. Main thing that is important, may seem obvious, but is not, as we will see with TCP, is that UDP is message-oriented. What does this mean? It means that the UDP service interface, the service interface, remember, is the interface that's offered to a higher layer, to an application program that's using UDP. Then if you use UDP as a programmer, you have the concept of a message. You write into UDP one message, and UDP will either lose the message because the packet is lost, or will deliver it. But it will not do things like serving half of a message, or the middle of the message, or only the end of the message, because it broke it into several parts. UDP may break it into several packets, but it will always make sure that the message as it was submitted by the sending side is exactly the ones that is submitted to the receiving end, which seems normal, but as we will see, it's not what TCP does. Right? UDP treats every message as one atomic entity that it has as a job to deliver. If you submit to UDP multiple messages, so if your application program calls UDP several times with different messages, UDP feels free to deliver them in any order. So there is no concept that the first message that you have submitted should arrive before the second. Although in practice, as we will see, this is often the case, but in the lab you will be able to see examples where this does not necessarily happen. And also with UDP, of course, you try not to lose messages, but UDP does nothing to protect against losses. When you send a message using UDP, if the message is lost, you will not notice, or UDP will not give you a notice that the message was lost. There is no, if you look in the header of UDP, there is the source and destination ports. There's the length of the message, a checksum that verifies that there is no bit error in copying the bits, similar to the CRC, less powerful than the one we've seen in Ethernet, but similar in function, and that's it. So if this message is lost, and you receive the message before and the message after, there is nothing in the UDP header that tells you there was in the middle one message that is lost, which is normal because the semantic of the service offered by UDP is a single entity called a message. Now, if you do streaming over UDP and you care about detecting that some messages are lost, then you have inside the application layer to number your blocks, for example, to recognize whether something is lost or not. It's up to the application to do it. UDP does not do it. Contrary to TCP, that will do it for you. Here is how a programmer typically uses UDP if you use low-level interfaces, for example, like we will do in Python in the lab or in C, for those who prefer. So to use UDP, you must create first a data structure called a socket. This is similar to a file descriptor in Unix. It is a buffer, essentially, in which the operating system will store the data that you have sent before it's able to really send them, or that you are receiving before you're really able to consume them. So you need to instruct the operating system that will give you a socket number. Then once the socket number is given, you have to what is called bind it. Bind it means give the address on which you want to use it. So by default, you don't need to give anything, but you may have a machine that has multiple IP source addresses because you have multiple interfaces, in which case you may want to associate this UDP message with one of your source addresses, and you also want to give the port number, the source port number. So if you don't know which source port number, you just do a bind with no argument in the port number, and the operating system will return the one port number from you. Once you have done this, you're ready to send. And a simple function for sending in Python or in C is send to. The semantic means, because of the to, you have to pass as argument the message, but also the destination IP address and the destination port number. So a same socket can send to multiple destinations. In every message, you have to specify to whom you send it. And that's all that you can do. That is on the client. On the server side, the server is something that does the following thing. You do the same creation of socket and binding of the port number. But on a socket, you can do send, in which case you are client, or you can do receive. Receive means you say to the operating system, now I'm waiting for data to arrive and wake me up as soon as something has arrived. So by default, a receive is blocking. So when this code instruction is executed, if something has arrived for you, you will get as a return the message that has arrived. If nothing has arrived, then the program blocks. I said receive, in fact we say receive from, because by default UDP does not have the concept of who is sending to you. If you're a DNS server, you may receive a query from a very large number of machines, so the source address will be, which is in the source address, which is in the IP header and in the UDP header for the source port number, is passed to the application program. So we say receive from. So what is returned here is the message and the identity, IP address, and source port numbers of the sender. So that would be, for example, a simple program that sends something and receives it and perhaps display it on the other side. If this message is lost, this program will do nothing. So if this message is lost, then it is lost. The receiver will receive nothing. We say we have a server here because it's waiting for things to happen. TCP-IP communication is typically client-server mode, even when it's peer-to-peer. The only way we know so far for A and B to communicate is one of the two has to be, for whatever reason, in listening mode, and the other can send. Right? If both wait for each other to send, then we have a deadlock. So it's why we always have a server side in communication. And peer-to-peer means simply that you are both client and server. There are phases when you are listening and phases where you are sending actively. Sometimes you hear the concept of a connected UDP socket, which leads to a lot of confusion. Therefore, I'll say a few words about it. UDP is essentially connectionless. It means the protocol UDP, which is essentially void. There is no real protocol in UDP. UDP simply means I send you one block of information, and before sending it to you, I don't need to inform you that I will send you something. Right? Like you do in the UK, for example. If you send a parcel to someone, you need to have their zip code number, which identifies practically the block. And in order to know the block, you need to call people or send a mail to know their block number. In UDP, you don't do that. In TCP, we'll see, we do that. We have first to establish some overhead information. In UDP, we don't do. So UDP is essentially connectionless. However, we find the concept of connected UDP socket, which is simply a cache, where if you're tired of always saying send to, if you're streaming information and you always send the information to the same other end, you don't want to always say sends to for the 1 million packets you will be sending. So you can, what we call, connect the socket. Connect the socket means associate once for all that the destination address for this socket is the one I am giving now and the destination port number. So a connected socket can be used with a send instead of send to, and if you use send, it will automatically go to this one. And conversely, on the receiving end, if you receive on a connected socket where you've said whom you would like to receive from, then you receive only from this, and you can make it such that you can receive only from this one. So that's a programming facility, but the protocol fundamentally is connectionless in the sense that when you do connect here, there is no information sent to the server. You're not talking to the server and say, hey, I will send you something. You're just instructing a cache in your operating system to say the destination address will be this. If you look in detail what you need to do as a programmer, when you call the socket, here those are abstract, easy views. Of course, when you do it in a concrete programming language, it's always more complicated. In particular, you have to specify whether the socket you're creating is IPv4 or IPv6, which seems to be perhaps contradictory to what I said a minute ago. I said there is no UDP-v6 and no UDP-v4. It is true in the sense of the protocol. Again, in UDP, there's no real protocol. There's only a message format. The UDP header is the same, whether you use IPv6 or IPv4. However, the IP packet is not the same. And because when you use the socket interface, you have to say things like, what is the destination address? If you use a program, a socket call that is made to accept only IPv4 addresses, then it won't work with IPv6. You cannot simply give an IPv6 destination address into an IPv4 socket. It won't work. So the addresses are visible to the code, even if we have a nice layering of things. And the downside of it is that the sockets have to be aware of IPv6. So there are 3 types of sockets you can use. You can use IPv4 sockets, IPv6 sockets, or on newer systems, you can use socket interfaces that are able to use either IPv4 or IPv6. You will be able to exercise all this in Lab 3. Right. How do you know whether you use UDP over a socket that is v4 or v6? When in principle, it's DNS that will help you. So your application program, the first thing it has to do is to call, when you connect to a machine that's identified by a name, you need first to find what's the IP address. So by going to DNS, you can use a DNS function that will first try an IPv6 address, and if it doesn't work, try an IPv4, or you can ask directly, give me all the addresses that there are, and then your program can analyze whether you have obtained an IPv4 or an IPv6, and then I can decide to continue with whatever address I want. That's the ugly part of programming with sockets today. You always have to manipulate this duality of IPv4, IPv6. Modern operating systems like iOS for the Apple devices mandates that everything you do has to be done in this way. It has to be working with IPv4 or IPv6, and the software has to be able to handle all cases. Android doesn't do it. So in Android, you have applications that work only for IPv4. In iOS, it's not the case today. But that means if you're developing an iOS application, you'll have to use sockets that manipulate all that stuff. Here is a mental model of what the sockets are. They're not just an abstraction for the programmer, but they have some existence in the operating system. A socket is essentially buffers that are allocated to a given user by the operating systems. And when you send data, the data is put in the buffer, and then until the operating system is able to pass it to the Ethernet or Wi-Fi adapter, for example. And it's also served in the reverse direction. When data arrives, then the operating system separates the IPv6 and IPv4 packets. I mentioned already that IPv6 and IPv4 are really treated as 2 different networks by all systems. So if an IPv4 packet comes, by analyzing the destination address, which hopefully is your destination address if it has arrived to your machine, and the port number, then it will be given to a socket that is bound to this port number. This is why we need to bind a socket with a given destination port number. And then it's put in a buffer, and it's up to the application program to consume the data from the buffer by doing a receive from statement. If the packet is an IPv6 packet, it's put in different sockets. So 2 sockets that have the same port number, but have different IP addresses, for example, IPv6 and IPv4, are separate sockets, or different sockets here. I mentioned that UDP sees messages as one single entities. UDP accepts packets messages that are longer than the maximum IP packet. The maximum IP packet is typically 1500 bytes, but with UDP you can create a block that is 2000 bytes, for example. It will be treated as a single message. In that case, there will be what we call fragmentation at the source. The source UDP datagram, the message is called a datagram, will be fragmented into multiple IP packets and will be reassembled at destination. We'll talk about fragmentation and reassembly a bit later when we come back to this topic in the module IP3. Quick question. What happens to Lisa if one packet is lost? I close the poll. %100% on answer A. So, yes. In fact, when you do a DNS resolver, then you have to do things a bit like TCP is doing. In particular, you need to start a timeout. This is very similar to what we saw as the stop-and-go protocol. So when you send a packet and a query and there's no response, you send it again. What DNS resolvers typically do, they have multiple DNS servers. So if you send to the first address and you had no response, you will try another address. Instead of retrying with this one, we'll try another address. And if it fails again, you might retransmit again. And when you retransmit, then you may need to be careful about a few things. What can go wrong if you have an application program that does exactly the stop and go protocol? Transmit, wait for a timeout. If the packet is lost, retransmit. What could go wrong with that? Yes?
Timeout might not be long enough.
The timeout might not be long enough, in which case you have spurious retransmission. That might happen, but hopefully you have some measure of the round-trip time or some conservative measure of the round-trip time. If you have a fixed timeout, which is long enough, there might still be a problem. This problem is called congestion. If the other end, or the network in between, does not respond, drops the packet, not because it doesn't like you, not because of, doesn't like you means access control or lack of authentication, or not because of transmission errors, but because of congestion. Buffers are full in a bridge or in a router, or the server at the end is congested. So when you contact someone who is congested, you ask a question, the guy doesn't answer because he's busy doing something. What do? Do you ping the question constantly? No, probably you try once or twice. If you see the guy doesn't respond, you calm down and you wait until the guy is ready, right? And there's a good reason for that, is you just make people nervous if you do that, because you increase the congestion by. So if a system is congested and you continue to submit it to a constant load, you can perpetuate the congestion. So you will have problems. We'll come back to that. That's the topic of congestion control in the internet. That will be module 5. But that is something that will be visible also already in TCP in the form of congestion of the other end. If the DNS server is simply congested because it cannot handle all the packets, if everybody who's trying to contact it retransmit at a constant rate, it looks like a denial of service attack. So typically what you do is you back off, you transmit, and if you have to retransmit, you increase the timeout such that the next time you will wait more and more and more so that the rate at which you transmit is decreasing over time. That's similar to something we have seen in CSMA-CD. When we retransmit after a collision, we have exponential backoff for exactly the same reason. We're ready to restart. Now let's move to TCP. TCP does a number of functions that have to do with reliable delivery of data, but also congestion control. Today and next week, we'll talk about the first, reliable delivery of data. We'll talk about congestion control a bit later. It will be a topic of its own. So we'll come back to TCP in another module. So as we know, packets may be lost, rarely, hopefully, but we can't guarantee that there is no loss. And in bad circumstances, the losses may be 10%, worst case, for example. So this occurs for a variety of reasons, but the good reasons are typically buffer overflow and transmission errors. With wireless systems, physical layer errors are in principle handled by the coding of the physical layer, but the wireless channel is random, so this is not perfect. We've seen also there can be collisions in some cases. And buffer overflow, we know from bridges and routers, can occur because those are queuing systems. And this will be precisely the goal of congestion control, to avoid that buffer overflows are too bad. But they occur, and something must be done when a packet is lost. TCP solves the problem once for all, in the sense that if you use TCP as a programmer, you can ignore the fact that packets can be lost. You cannot ignore it entirely, in the sense that if things go really bad, for example, if the destination server is destroyed, doesn't exist anymore, then everything is lost and there's nothing that TCP can do to repair the server. So you may still have a TCP connection that's hanging, that doesn't work, but TCP is doing everything that can be done to repair the losses. So as an application programmer, you don't. To do this, it does it in a special way, which is driven by history. TCP is offering sometimes what is called a virtual circuit service. The very old computer networks, they lived on the principles that you would establish a circuit, a physical circuit in some cases, from a source to a destination. The property of a physical circuit is that data can be lost if there are transmission errors. For a physical circuit is what you do when computer A calls computer B over a telephone line and a modem, for example. Today that's very rare, except perhaps over satellite links. Then when you do this, packets are always delivered in sequence, in exactly the order that they were transmitted, with possibly some loss, but there is never reordering because a physical circuit is transmitting the bytes in the order that they are transmitted. And TCP is emulating this. It's providing exactly the same thing over the internet, so it provides in sequence data delivery without loss. Right. So the in sequence is an addition. We will see a bit later that if you want to do away with that, you have to make your own application layer environment. Right now, let's record that the job of TCP is not only to deliver things in the order without loss, but also exactly in the order that they were submitted by the source. How does TCP work? Well, it's essentially very simple. You put a number in every TCP packet called a segment. And then you check whether the packets are received without gaps in the numbering. For this, you use acknowledgement. Whenever the destination receives a packet, it sends an acknowledgement to the source saying, I have received this packet at the source. Then you know the packet numbers, and then you can see whether something has been lost or not. This is what we saw essentially for the stop-and-go protocol. So TCP uses the same original building block, but we will see that there are a number of small details. The only coding that TCP does is retransmission. So TCP is not smart. It's not trying to use read-Solomon code to send 5 packets into 7 and things like this. It will, one by one, number all the packets. If one packet is lost, you retransmit exactly this packet. I said that the numbering is per packet. In fact, this is not true. TCP numbers per byte. This is a reminiscence of the fact that TCP thinks as its job as delivering a byte stream. In fact, a TCP socket from the operating system is very much like a file. When you read from a TCP from a file, you have to open the file descriptor and then you can consume the bytes one by one from the operating system. You do the same thing over a socket that is used to receive data from a TCP connection. Here is an example where the first packet is sent and the sequence number contains all the bytes that are in the packet. The typical packet capture convention is to put the last number is the next byte. So when I say 8001 to 8501, there are exactly 500 packets. This is because by doing the difference, you will get exactly the number of bytes, and this is the first, and this -1 is the last byte in the packet. Then when B receives, so this is of course in the TCP header. So unlike UDP, TCP adds numbering information in the header. When B receives this, it will send an acknowledgement to A saying, I acknowledge the largest number I've received here, which is in that case 8501, the last number plus 1. So the semantic is that the next number I expect to receive. Then A continues and sends 3 packets of 500 bytes each. So this example is highly academic. It's just to make the explanation simple. It's very rare that an application uses to choose, or a TCP implementation sends packets of exactly size 500. So when you will do your own packet traces, you will see things a bit different. That will be in lab 5, where you will do your TCP traces. And here 2 packets are lost. So when B receives those 3 packets, then the TCP at B has a gap. So even though this packet sent at line 5, the 4th packet in the sequence has been received, it cannot be delivered to the data. So if the data does a receive or a read here at this point in time, it can consume the first packet, 8,000 to 8,500. But this one is invisible to the application because delivering it to the application would violate the sequence. So it is as if they had not been received. Then B will send an ACK of what has been received. So we'll see that the ACK field is a very primitive way. We'll see a better way in a second. The ACK field simply ACKs the largest number received in sequence. So I have received something. Here I repeat the same information. Bad luck, this one is lost anyhow. So since this one is lost, nothing happens here. The loss will be detected. There's a variety of mechanisms for detecting losses. Here I'm showing the simplest one, which uses a timeout, which is the less frequent case in TCP, but is a simpler and historically the first that was implemented. So when you send a packet, you start a timeout, which is larger than the round-trip time. So TCP estimates the round-trip time, puts an upper bound to it, and starts a timer. When a packet is not received, when the timer that corresponds to this round-trip time expires, time is ready for a retransmission. So here, there will be a retransmission of which packet? Well, of the last thing that this guy knows is not transmitted. So this guy doesn't know what has happened, in fact. The source just knows that out of those 3, I have not received confirmation. So it doesn't know that the 3rd one was transmitted, but it knows that starting at this number, there is a gap. So it will retransmit the first packet that was transmitted. And then if it's lucky, there will be an acknowledgement that this packet was correctly received. And then the next one here will be retransmitted. We see that when this packet is received, then the data of this packet can be delivered. And again, this one cannot be delivered. When this second lost has been repaired, then the application can receive all the data, including the data of the 3rd packet. It is only when this loss is repaired that this data is available. Right. This is what happens because of the semantic of doing in-sequence delivery. Of course, what has been shown here is a bit primitive, and the very first version of TCP works in exactly this way. But we can improve things a bit. For example, we can pass information, selective information to the source about what has been lost. So this is called selective acknowledgement, SAC. So there are 2 fields that talk about acknowledgements in a TCP header. One is the ACK field, another one is the SAC field. There are 2 fields because historically only the first was present. So here I'm assuming when receiving this, B sends an acknowledgement saying, I have received everything up to this number, and also I have received this block. Right? So now the source knows exactly what went wrong. It knows that this block of 2 packets has been lost. So it will retransmit. Now, what will the source retransmit? It depends. It depends on which version of TCP you're using. There are a large number of different subtle options that may be used or not used in TCP. Even if you use the same version of Linux, depending on which socket options you use, you may or may not use one of the tens of possible options. So one of the options that you can use is that you can allow TCP to repacket the data very aggressively. Remember, the job of TCP is not to deliver a message, but is to deliver a stream of bytes. So there is no constraint on TCP that it transmits the data in packets that correspond exactly to the submission of data by the application. So here perhaps the application did 4 consecutive writes into the TCP socket. So it wrote 4 blocks of data. But TCP doesn't feel that it has the job of delivering exactly those 4 blocks as they were written. It just has to deliver all the bytes that have been submitted here. And this is visible here, for example, when it does a retransmission, because these are small blocks. It's possible to put several of them in a single IP packet, so TCP will do it. If it has to retransmit, it knows it has to retransmit 2 packets. There's no reason to do 2 packets. You can do only 1. Some implementations will do 2 because they are lazy, or you have used the options that prevent them from repacketizing. But in principle, they should be able to do this. So that will save 1 packet. When this is received, the loss is repaired, so everything that has been received is delivered, and the next ACK that will be sent is an ACK for the last thing that was received, which is here, the highest number. So I would say that's the standard operation of TCP today. We see that the loss was detected here before the timeout occurs. It was detected by receiving something that indicates that there is a gap here. We will see that in practice it's a bit more complicated. You don't immediately retransmit when you have a gap because there might be reordering of a few things, so we will see exactly how this is done in practice. Now, a consequence of this mode of operation is that TCP needs a receive buffer. As we have seen before here, for example, when a packet is received and everything is in sequence, it's put in the receive buffer. We still need a buffer for one reason, is that the application may not be able to read the data. Why could that be? Why is it possible that the data has reached a machine and the application that's supposed to read it is not ready to read it, so it won't read it on now? Yes? Because? There's an error in the packet. Yeah, that's the worst case, but the more standard case, yeah, it's busy doing something else. Or perhaps the previous packet was asking to do an SQL query. You know, SQL is dramatically slow. You need to take tens of seconds to know exactly what's the result of a given table. So perhaps the last packet calls the operation to a very heavy operation, and the program is busy doing it. In the meantime, other packets are coming, and the program needs to complete the operation that it's doing before getting to the point where it does a receive from. Of course, you try to avoid such problems as much as possible by parallelizing multiple threads, but you can't avoid the fact that the speed of the application is not under your control. And the speed at which you receive data is independent of the speed of the application. So you need a buffer to decouple the two. That's an important thing. We'll see you need a buffer, and you need a way to make sure this buffer doesn't overflow. So you have a receive buffer. Worse, you may have to put things in the receive buffer because they are out of order, which is the case of this packet here that was received out of order. So this packet is kept in the buffer, but in some sense it's secret to the application. If the application does a read, it can read only this. This one it cannot read. But of course you don't drop it. At the receiving end, when you have received data, even if you don't deliver it to the application, you keep it. And when the loss is repaired, then of course this application will be visible. So you need a buffer for that. Now if you have a buffer, you have a problem. A buffer is a solution to a problem of mismatch of rates. We've seen that buffers exist in bridges and routers. Here the mismatch of rate in bridges and routers are typically due to what? Here in a TCP case, the mismatch of rate is the rate at which packets arrive from the network, namely from the source perhaps, and the rate at which the application at the receiving end is able to consume them. Why do we have also a similar problem in a bridge or in a router?
Because it has the capability of processing the data and putting it.
Because it doesn't have the capability of processing the data. That can happen, but it's a low performance bridge or router. That means the CPU is limiting. It's not able to analyze the packet header fast enough to propagate them. That can happen in software bridges. If you do in Mininet, so those things could happen. But in a hardware bridge, in principle, you make sure that doesn't happen because you can do processing in dedicated hardware. Yes?
Because one of the other nodes is too slow and cannot
because one of the link to the other node is too slow. So typically, exactly that's the case. If you have a router that has 10 input ports and 10 output ports, if all ports are at the same speed, let's say at 1 gigabit per second, if all the traffic coming from the 10 inputs goes to the same output, then you have 10 times faster inputs than you have output. So somewhere you will have a flow problem, so you will need a buffer. If you could guarantee that all the inputs have an aggregate rate that is less than the total rate of the outgoing link, that you would not need a buffer, or you would need an extremely small buffer. But this is rarely the case. So if you have a buffer, you have to make sure it doesn't overflow. So one of the problems is the hanging problem. So assume for some reason there is an adversarial loss process that keeps killing a packet and its successive retransmission. So bad luck, you transmit P0, it's lost. You continue sending a number of packets, then you retransmit P0, it's lost again, etc. What will happen if you do nothing? Then you have to store in the resequencing buffer all the data that has been received, P1, P2, etc., Pn plus 1, because you cannot deliver them because they are out of sequence, P0 is missing. So if you do this stupidly, as I said now, then you will have potentially a need for an unbounded buffer here. If it happens that P0 is lost many times in a row, you will need at least a very large buffer. That's the first reason that motivates to put a limit on the number of packets you can send being in parallel. This is called the window. The window, a synonym is the number of data on the fly. So here P1, P2, etc., Pn are the data on the fly. There are data that follow P0, and they are, if I allow them to be unlimited, then I may also require unlimited buffer space at the other end. So to avoid this, we put a limit, which is called the sliding window, which seems to be complicated because that's a detailed cartoon, but in fact is very simple. For example, here I assume I have a window of 4, or let's say 4,000 bytes, and every packet is 1,000 bytes, so it's exactly 4. The window in TCP is in bytes, because in the resequencing buffer, we put the things per byte. So if the size that matters is bytes. But to simplify the story, I would say it's 4 packets here. So here I assume I have a window of 4. That means that I can send those 4 packets, whatever happens. So I can send packet 0, 1, 2, 3. But then in order to send packet 4, I must make sure that packet 0 is acknowledged. So I am rid of packet 0. Packet 0 doesn't exist for me anymore. It has been acknowledged. That means it has been safely received. Then, so here let's see what happens. So when I've sent s equals 0, I'm showing the window with the solid frame, and the shaded area is the part of the window that contains packets that I may send now. And here I'm assuming there's no loss, so every packet will be sent on enough. I've sent 0, so it cannot be sent, but the window doesn't move because I have not received an acknowledgement. When I receive the acknowledgement for packet 0, and the acknowledgement means it has been received in sequence, right? For the window, it is the ACK field, which means not the SAC, means it is received in sequence. Then I don't need to worry about resequencing, so I can now I can move the window, and I can send 1, 2, 3, 4. And now we see what happens when I send packets. For example, 2, 3, 4, 5 have been sent, but not acknowledged. Therefore, I'm blocked until I receive 1 acknowledgement. And here we have a period of time where we have a synchronization of the destination and the source, where the destination acknowledges packets 1 by 1. So whenever 1 is received, then we can move the window and send 1 packet. So this is how the sliding window works. We can send only 4 packets starting from the first non-acknowledged packets. So if we use this mechanism, what can the sender do at time t1? I close the pool. And the majority is right. Of course, here, the fact that this one is lost prevents us from sending a fourth one. The selective acknowledgements are useful perhaps for repairing the losses, but the semantic of the windows is everything that has been acknowledged in sequence, right? So consecutive numbers. So we cannot send packet 4. The window is necessary to avoid that we have an arbitrarily large number of packets to be stored at the receiver due to the resequencing problem, but it's not sufficient. Still, with a window, you may still overflow at the receiver. And what could be the reason? Well, it's again a slow application. So here I'm showing an example where there is no packet loss, and a window of 4 again, so everything is nicely acknowledged and everything is delivered in sequence, but the application is not ready to receive it. So it will not be in the underground part of the receiver, it will be in the visible part of the receiver buffer, but it is still there hanging in the buffer. Now the buffer, remember, TCP is in operating system, it's in kernel space, so it's using resources that are not as large as user space. And you want to make sure you get rid of those as quickly as possible. So if the application is very slow, and it could be simply because it's temporally slow, or you have a server that's overloaded by a large number of clients, for example, then this might happen. The socket buffer might overflow. And what do you do when the socket buffer overflow? Well, you're in trouble. You're in trouble because if new data is coming and the buffer is full, you have to drop something, which is the most stupid thing because those packets have managed to find a way through the hostile internet. They've gone through congestion, transmission errors, and all that stuff. They've arrived at the server, and there you drop them. So that would be foolish. We want to avoid this. So we need a way to avoid this, and this is called flow control. So flow control is the name is important. All those things seem very similar. Congestion control, flow control, window, those are different things. So a window is simply saying, I put a limit on the number of consecutive data that can be on the fly. Window flow control is the function that we do, or flow control in general, is the function that we do to prevent overflow of a receiver by a sender. So that's something you always need to do. If you do an application program from A to B, not only you need to repair the losses, but you need also to make sure the receiver is able to handle them. If you are Google streaming, if you're YouTube streaming video to a very low-end receiver that has a hard time receiving it and decoding them, there's no point bombarding the receiver with 1 gigabit per second that it cannot consume, for example. Most often it occurs in the reverse direction. You have a lot of clients going to a server, and then similarly, you want the server to be paced, you want the clients to be paced by the capabilities of the server. So that is the function called flow control. Adapt the sending rate of a source to the speed of the receiver. That is different from congestion control. Congestion control is more global. If you want, flow control is an element of congestion control, but practically in the internet they are separated. Any end-to-end thing has to do flow control. If you use TCP, you rely on TCP to do it for you. If you don't use TCP, if you use UDP for doing a streaming application, you will need to do flow control in your UDP application. Congestion control is about preventing problems in the global internet, in the bridges, in the routers. Make sure that the buffers there that are everywhere, that they don't get overloaded and that the losses don't get dramatically bad. As we will see in the congestion control module, if we allow sources to send as they want, we can create dramatic cascading effects that will make losses very, very large and bad for everyone. So you need to avoid this. Whenever you send through the internet, you have to do congestion control. You have to make sure that you don't flood the network with data that will be lost and that will cause others to suffer from losses. So it's about adapting the rates of source to the state of the network. We'll see that TCP does it, but it doesn't do it with the mechanisms we'll see today. So the flow control mechanism of TCP is called the window field. The window field is the field that is sent by a receiver to a source to indicate to the receiver what is the size of the sliding window that this sender can use. Before we had a sliding window of fixed size 4. Now we see that in fact in every acknowledgement the receiver is signaling to the source the size of the window, and it varies from 2 to 4, which is perhaps the maximum size, to 0 in one case, which means you're shutting down the receiver. And you see that the receiver of course has to adapt and may send more or less depending on that. Why would we have this behavior here? Well, this is revealed by zooming on what happens on the receiver side. Here I'm showing on the receiver side the receive buffer. So here I've received 2 packets, packets -2 and -1, and there are 2 available slots in the receive buffer. So what this receiver is signaling to the source is the number of free slots in the receive buffer. And now we see here, for example, that the receive buffer is full, not because of losses or any retransmission problem, but because simply the application didn't consume the data. So if the buffer is full, then we signal this to the source by sending, well, window equal to 0. Then the application reads, and then when this changes, you may or may not, depending on the implementation details, you may send a new acknowledgement with a change of the window. Of course, you need to be careful when you send a window of 0, what kind of bad things might happen. Yes?
If the subsequent ACK is lost,
Mm-hmm.
we won't get any data.
Exactly. If the subsequent ACK here is lost, then we're in a deadlock situation. I mean, a window of 0 is a stop signal. If you send a stop signal and this stop signal and all the subsequent signals are lost, then in principle an application sends ACK when it receives something. So if this guy is not sending because it stopped, and this guy is not sending ACK because it doesn't receive anything, then we have deadlock. So of course you need to avoid it. Typically, this is avoiding by, if you are a receiver, a sender, and you have a window of 0, you are still allowed once in a while to send 1 packet, just to test the water, and so violating the window. So a window of 0 is never taken seriously. You take it once in a while to be a window of at least 1 maximum size packet. And similarly, on the destination side, if you send a window of 0, there should be a timeout that forces you to reconfirm this window of 0 once in a while by sending acknowledgements that perhaps will do different things. Now, if we put things together, we obtain this figure that is exactly the same as what we've seen before, except now that the 2 directions are together. Before, I had a sender on the left, a receiver on the right. I did that on purpose to make the story easier. But in reality, TCP is bidirectional. The same system can be both source and destination. So there is a sequence number space for each source, which is visible here. So A sends packet in the 8,000 something, and sends a window. Here the window, that's the window field for B when B acts as a sender. And B responds with TCP packets that contain some data, have an acknowledgement. Now the acknowledgement is about the numbering space that was sent by A, and a window that will be used by A to know the size of its sliding window. So those 2 are visible, and they are both in the packet headers. And an ACK has to do, when you have an ACK followed by a number, the ACK number has to do with the reverse direction. Similarly for the window, but the sequence number have to do in the direct transmission case here. So the 2 directions always exist together. In particular, I mentioned in the previous slides that destination may send an acknowledgement. Well, an acknowledgement is simply an empty TCP segment. TCP segment means TCP packet. If you have nothing to transmit, you still need to transmit acknowledgements. So acknowledgements are simply fields in the TCP header, and they can be empty if B has nothing to say, or they can contain information. Typically, most packets are empty in one direction. For example, if you connect to a web server and you download a large file, then you have lots of packets coming from the web server to you, but from you to the web server, there are empty TCP segments that are used only for acknowledgement. So, and if those acknowledgements are lost, it has the same effect as losing a packet. Right? So we always see some traffic in the reverse direction. That's the cost of TCP. TCP has a large cost in a number of aspects that we will discuss in detail. A little question on what it means to control traffic with a sliding window. So I'm assuming here a very idealized case where I have a single channel over which I use TCP, a fixed round-trip time. In reality, the round-trip time varies a lot because it includes also the processing time at source and receiver. And I have a fixed window here. Right? If I do this, and I also have a channel capacity C between the two. How do the two combine? How do all those elements combine? I close in 5 seconds. And the majority says A, which would make your physics teachers happy because it's the only formula that respects the units. So this is in seconds, let's say. This is in bits per second. So the result is in bits, which is a window is in bits or bytes, if you prefer, units of data. But this is the correct answer. We see that if the window is too small, we will be a bit like the stop-and-go protocol. When the window is too small, we waste some time waiting for acknowledgements to come. If the window is large enough, then we have a pipeline and we can continuously transmit. And if you do the math using this reasoning, you see that the window size that you need is the bandwidth delay product, in fact. So we come back to our very first considerations of the first module. We see that the bandwidth delay product shows up here and is another motivation for having a window in TCP. Instead of doing the stop-and-go protocol, which is very inefficient as soon as the bandwidth delay product is large, then you solve the problem by having a window, pipelining the data. If the window is large enough, as large as the bandwidth delay product, then you're able to send at the full capacity of the channel, which is another motivation for doing things the way TCP is doing them. Right. So this is our first pass on TCP. We will come back to several aspects of it, in particular in congestion control, which is perhaps the more complicated part of TCP. There is also a huge number of additional small or less small algorithms in TCP. Many of them are experimental or are obsolete. I mean, TCP is the largest subject of research in the, say, the lower layers of the internet. So there's a huge number of papers on TCP, and believe it or not, people are still working on developing new versions of TCP today. In the labs, we will see TCP cubic, TCP data center TCP. Those are two examples. So this is constantly being changing. This is a moving target. I'll just try to give a hint of the various reasons for doing things. One of the things, let's go through this first. So one of the bad sides of TCP is that TCP requires a handshake before starting the data. And the main reason that was advocated for having that is to agree on the sequence number. So a typical TCP implementation will start with a sequence number, original sequence number that is drawn randomly to avoid replay attacks, for example. And then the destination needs to know what is the initial number. So in order to know that, you do a handshake. Also, you need to create a socket of the receiver because you need to create this resequencing buffer and all the mechanics that goes with that. So this is typically how TCP is used. In blue is sending data with TCP. But before doing that, you typically, on one end, sends a special empty TCP packet, which is called a SYN packet. In the TCP header, there is one bit somewhere, which is called the SYN bit. If it is set, if it's equal to 1, it means it's a SYN packet. That normally occurs only in the first packet in each direction. And it has a sequence number. This is the original sequence number. Then the other side, that is the server side, if you're a server, that means you're waiting for SYN packets. SYN packet means connection opening packets. Contrary to UDP, remember UDP, we said we send to UDP without warning. Here, that's the warning. SYN packet means I would like to send you something. And normally, what the server does when it receives a SYN packet, it opens a socket for this guy and reserves some data structure. Then this is acknowledge, which serves as a confirmation. And the acknowledgement is acknowledged so that the server knows whether this packet is lost or not. And when this is received, the connection is established on the server side. The connection is established on the client side as soon as the SYN ACK packet is received. So in the packet capture or in the literature, this is called a SYN packet, and it's called a SYN ACK packet. Right? The SYN packet is the only packet that doesn't contain an ACK field. All TCP packets have an acknowledgement number, except this one. Right? So there is a bit in the header that says whether there is an acknowledgement or not. And only after that you can transmit data. For breaking the connection, because you use data structure in the sender, in the traditional way of doing things, which is also called hard state, you want to release the data. Release the data means get rid of make the buffer available again for the rest of the machine. And in TCP, this has to be done explicitly. It's done explicitly by sending a close that is also acknowledged. Now, a close, because in TCP there are two directions, you have to close the two directions. And you might have weird things like a connection is closed in one direction and not the other. So this is the last century way of doing things. We will see a bit later a new way of doing things. I say last century because we keep hard states, which has a lot of potential drawbacks. In particular, if anything crashes in between, we have to recreate the state, which may cause considerable work. Yes?
Why does the other node send two separate? Why does that enhance by just send?
Here?
Yeah.
This is in the case that this is not closed. So this connection is closed, but the reverse direction is not. Perhaps because there is some data that still needs to be transmitted here. So the application has done a write block, and it's not entirely transmitted, even though the application on this side is doing a close. Right. It's a bit weird, I admit, but this is possible with TCP. Here is the TCP header. It's at least 20 bytes, right? So the IP header is 20 bytes with IPv4, 40 with IPv6. So to transmit one bit of information with TCP and IPv6, we need 60 bytes of header, right? So if you have a thermometer on your radiator that is transmitting the temperature every minute, it needs to transmit 60 bytes of header to transmit one temperature reading, which is probably coded on 1 byte. That's highly inefficient, and there are mechanisms to compress all this for Internet of Things, where you can compress all of it. But by default, if you don't compress, you have the 60 bytes to pay for with IPv6. The TCP header contains the source and destination port numbers, which are the same fields as in UDP, though the UDP and TCP port numbers are different things. UDP port 53 has nothing to do with TCP port 53. Nothing to do in the sense that two different sockets will consume the data for those two ports here. And it contains the ACK number and the sequence number, which are 32 bits, the window size, all of this we have seen, a checksum like in UDP, and the options that are, for example, the blocks of selective acknowledgements. These options can take a large space here, for example, because you have selective acknowledgement. You may be acknowledging blocks that are not contiguous. If you lost 3 packets and the received packets are not contiguous, then you have to describe that. And TCP standard says that you can have up to 3 SAC blocks to limit the size of the header. Time's out. That's all for today. We will continue discovering TCP next week.